going to need the work that you did on the previous page, 538. Okay, I'm going to go ahead and say pause right here, maybe write what I wrote in the answer space for 539, but then let's talk about it, okay? So pause, write, and then resume, and I'll talk you through what's going on. You paused. Thank you for doing that. Let's go. So the side length ratios from the triangles in our table, the ratio of the length of the side opposite angle A to the hypotenuse is the side opposite angle A to the hypotenuse is 0.7 or 70%. Although honestly, 0.7 is the better answer. So 0.7. There are more decimals to this on a typical 45, 45, 90 triangle. We'll get into that. But for right now, knowing that that 0.7 is the ratio result is the important part of activity 1. The ratio of the adjacent side to the hypotenuse is adjacent side to the hypotenuse, also 0.7. 0.7. This is not always going to be the case. However, for us, because of the 45-45 degree relationship, our side opposite angle A and the side adjacent to angle A will have the same value. This is an isosceles right triangle. So therefore, these two sides, when you use them as fractions with the hypotenuse, they end up creating the same fraction. And that doesn't matter what size triangle we use. So if you did make a 1 inch by 1 inch triangle, or even a 1.5 inch by 1.5 inch right triangle, we would have the same ratio of 0.7, or the other ratio, 0.7, because the sides of the 45-45 degree right triangle are the same. Question 8. Compare your measurement and ratios with those of your classmates. We should all notice that the sides of a 45, 90, in fact, a better word than side or line would be leg. Right, so there's leg, adjacent side, and leg, opposite side of angle A. And those legs, when you make them into a fraction, they will create a ratio equal to 1. Just like in our picture or at the end of our table here, the sides that are opposite divided by adjacent would be this side length divided by this side length, and they were the same number. So when you divide one number by itself, of course, the result you're going to get is 1. Why do you think that you and your classmates have the same answers? Why didn't this happen in the first one, the getting started? Remember in the getting started, what we did in that one was just do it for any old random triangle. And in that one, it wasn't a 45, 45, 90 triangle. So the relationship of the legs isn't going to be the same and consistent. Here's another question. What reasoning supports how you wrote the first proportion, the 0.7? And it's all based upon the measurement that the side opposite angle A is 70% of the length of the hypotenuse. And the same thing is true of the side adjacent to angle A. It's going to be 70% of the length of the hypotenuse. With that, let's go ahead and take a look at the worked example. Given the same reference angle, are each of the ratios you studied constant in similar right triangles? And you can investigate this question by analyzing similar right triangles with outside measurements. So we have a triangle. We have triangle ABC and triangle ADE. I'm going to call out that this is the reference angle. We're going to consistently stay with angle A as the reference angle. This is the side that we're going to call the hypotenuse. This is the side we're going to call the opposite side from angle A. And in the smaller triangle, this is the side opposite angle A. I really do want my highlight color scheme to match. I want to be consistent pretty much this entire module. The rest of this topic, I want to be consistent with my highlight scheme so that you see what I'm talking about faster and more deeply. This is the adjacent side along the bottom, AE. but also AC, depending on the size of the triangle. We can write proportions, and we can write the proportions in this way. So if I look at the letters AE, that's orange. This is why the highlight is important. I'm going to highlight the AE orange. I can also highlight the AC orange. So I've made an orange-orange fraction. But if I rewrite them so that we have small to big triangle, AD over AB is the hypotenuse to hypotenuse for small to big triangle, then that arrangement, in fact, this deserves a zoom in for a second here. Okay, I'll be a little bit over the triangle space. Maybe I can do like this, move me down. Ooh, different corner. Okay, so in our arrangement of the triangles, we can write our proportions of just the orange fraction and just the green fraction. But I'm telling you, as this topic develops, we're going to want to do them differently. We're going to want to take the AE line segment and the AD line segment, which are both from the small triangle, and compare them to the AC line segment, leg, and the AB line segment from the big triangle. And this arrangement of the fraction is actually what's going to govern the math that we're doing in the rest of our topic. We want this, star it, less of that. It's not that this is wrong, though. This is okay. It's just we're going to be really doing proportions that look like this. An adjacent side compared to a hypotenuse for the small triangle, and an adjacent side compared to the hypotenuse for a big triangle. I do notice they say length of the hypotenuse, so I'm going to highlight that green. And they say the side length adjacent to A. This is going to be the much more preferred way to write your proportions, where within the small triangle you write a fraction, a ratio. Within the big triangle you write the equivalent ratio. So given the same reference angle measure, that was what I was saying like this, the ratio of the side length adjacent to the reference angle divided by the length of the hypotenuse is constant in similar triangles. This is a major idea. This is a worked example worth remembering. I'm in fact going to highlight this whole thing in pink because it is a very valuable worked example to remember. Thank you for watching this episode. I appreciate your work, appreciate your math thinking. We got one more page of notes I want to make sure I share with you from Activity 1, where we'll then wrap up the concept from similar right triangles that are 45, 45, 90s. I'll see you in the next episode. Like, comment, and subscribe. Bye.